After the break, all are refreshed to listen to the second talk by Dr. Sabaskar, lecturer, Department of Mathematics, Government Polytechnic College, Arandangi on neural networking. May I call upon Ms. K. Sumitra, Assistant Professor, Department of Mathematics, to introduce our keynote speaker and welcome him for the second day of ICRT-MCS 2023.
Participants, distinguished guests, and honored speakers, good morning. We are delighted to have you all here today as we gather for the second day of the ICRT MCS 2023. It's an immense pleasure to extend our warmest welcome to our esteemed invited speaker, Dr. J. Jabaskar, who has graciously joined us to share his knowledge and insights. Your presence truly elevates the quality and significance of this event. Dr. J. Sabaskar completed his PG Mathematics at St. Joseph College, Palayam Kotai, Tirunelveli, his MPhil and PhD at Pondicherry University, Pondicherry. He had cleared in GATE in the year 2009 and CSIR NET in the year 2011. He had worked as an adjunct faculty at NIT Calicut and as an executive engineer, software development at Kennametal India Limited. His area of research is in computational fluid dynamics. He has published various articles in reputed international and national conferences, seminars, and workshops. He has received a few awards and certificates for his academic and research excellence. We are truly honored to have such a simple and well qualified person amidst us as our keynote speaker. Now, I invite our principal, Sister Pushpa, to honor the speaker with a shawl and the vice principal with memento. Discussions that will unfold today. Let's make this event a memorable one together. The platform is yours, sir.
ஆன்ல இருக்குதா? Sure. So thank you for your warm welcome. Actually, so first of all, I thank all the conveners of this conference for inviting me for this wonderful event. Am I audible? Okay. So I'm Sabaska. So my lecture is going to be on graph neural network. So actually, this is one of the most active research area in deep learning. So now, so my lecture is going to be somewhat rich in mathematics because I'm from mathematics background. I don't know how many people are from mathematics background, but to follow my lecture, you should know at least some linear algebra things and at least some graph theory also. At least you should know what is graph and linear algebra concept like vector spaces and matrices. I think I assume that everyone have that knowledge. So first, PDF. I closed PDF. Huh? PDF. So both of these.
ஃபேன் இங்க வச்சிடலாமா உங்களுக்கு ஃபிக்ஸ்ட்
இல்ல இருக்கட்டும். கேக்குதா?
கேக்குது மைக்ல கேக்குது.
So my talk is divided into 4 sections. First one is why ML on graphs. So actually, where do these graph structure data arise? How we are going to process that? And by processing these kind of data, what are the information you are going to derive? And the next lecture, so next topic is, next section is AN, artificial neural network from perceptron algorithm. So perceptron algorithm is useful only for the linearly separable data. So, but so we have to extend these linear separable for these perceptron algorithm to the non-linearly separable data, that is through the artificial neural network. So I will give some basic introduction about the artificial neural network from mathematics view of. The next one is convolutional neural network. This is another important variant of neural network, which is specially designed to process the images. So the last or final one is the graph neural network. So here I will discuss how to extend these vanilla neural network to process the graph structure data, and I will do some recent research area also. So what are the issues in that and how the research is going around that. So, okay, with that I will close this session. First, so why ML on graphs? So here, so everyone came across the e-commerce websites like Amazon and Flipkart. So when you buy something from that website, it will automatically recommend some items to you. If you buy some items, it will recommend to you. It will recommend some items to you. How it is processed? See that here. So this is some data. So here we have 2 different characteristics nodes. So one is a different kind of nodes. One is users, and another one is items. Users have some characteristic vector, that is here see that male, here this is age, another one is geographical information. For each users we have some characteristic vector associated with that. Another kind of nodes, this is items. Here the items, each item has some price and brand and some offer and many things related with that. So we have many billions of users, billions of items. So what these 2 different nodes are connected, how they are connected? The connections are click, collect, cart, so add to cart and buy. So our connection is here, I'm talking about the graph theory. So we have graphs and nodes. Graphs has edges and vertices. Vertices are here 2 different kind of vertices. One is items, another one is users. So the relation, the edges are click, collect, add to cart, buy. So when you buy something, okay, it is recommending something. This kind of problems are called the recommender systems. So here we are using the session based recommendations. So when you log into your account, when you click some items, you are making some connection with that item. So your user is your node, and when you buy something, when you're writing some review, and when you compare something, you are making many connection between the nodes. The nodes are items. So when you are at the session, in your current session, you have created one graph around you. So the systems has to process these data, and it has to compare with other graphs. Already in their database, many graph structured data are available. Many billions of users, billions of items are there in their database. There are billions of graphs also. So you have created one graphs. The computer has to process your graphs, and it has to find some other graphs which is very similar to your graph. So then it will, when you buy something, it will recommend from the similar graph. Already they have the data, they have already the some history. From that history, it is suggesting something. So here see that the graph structure data are different for the computer, because computer can only handle numbers. It cannot handle the relations. Here the data is in terms of relation, so it has to process the relation, how it is going to process that relation. So many difficulties are there, how to overcome the difficulty, how we are going to construct some artificial neural network to process this graph structure data. I will discuss in the fourth section. This is the introduction for the graph structure data, how we are processing, and what kind of problem you are facing. So how to overcome that, we will see in the later section. The second section is going to be on perceptron and artificial neural network. So actually why I am giving some very basic introduction about the artificial neural network, because many of the peoples may be from mathematics background, so maybe they are not aware of artificial neural network in terms of mathematical background. So I am going to introduce the artificial neural network from mathematics perspective. See, first I'm going to start very basic the algorithm that is called the perceptron algorithm. So we have two different set of data that is linearly separable. Linearly separable means, so here we are talking about the two-dimensional data, so linearly separable by a line. So if you are talking about 10-dimensional vectors, base your data are 10-dimensional, you have to use a hyperplane with the 9-dimensional. The hyperplane with the 9-dimensional, why we are using the hyperplane? Only the hyperplane can divide your vector space into two regions. If you are using other planes like 8-dimensional, 2-dimensional, 3-dimensional, it will not divide the region your space into two regions. So always the hyperplane only divide your vector space into two regions. So we are concentrating on the hyperplane. So here it is a two-dimensional, so it is a line. So I have to find a line. See that here. So your data. So first we are going to assume that. So this. So actually here, this algorithm work only for the linearly classified data. So okay, here we have some data. So already this belongs to one class. This belongs to another class. This is supervised learning. Supervised learning means already why for the training data you know the answer. That is what means the supervised learning. So now we have some data. So my aim is I have to find out a vector. So for that vector, if you take the dot product with this data, data means here this is the vector. So if I take the dot product, so for this class it should give the positive value. For this class it should give the negative value. So you know that for dot product gives the cosine similarity between two vectors. So when the angle between two vectors is less than 90, you will get a positive value. When the angle between two vector is greater than 90, you will get a negative value. See that you can take this is your vector. So this is your vector, this is your data. So angle between these two vector is going to be less than 90. Here also this is negative 90, but cos will not take the negative sign. So always positive. So anyway, so for these all the vector dot product with W is going to be positive. Dot product with this vector is going to be negative. So I have to find out such vector. So the Perceptron algorithm says that. So if you first, it will initialize some vector. So you can take so you can take some vector here. So I initialized a vector from this. So now take this is your hyperplane which is perpendicular to this vector. If you take the dot product between these two vector, you are going to get a positive value. But if you are using this vector, this data, when you apply the dot product, you are going to get the negative value. But your data says that already this is belongs to one class, both are from the same class, but you are getting negative value. So it has to adjust your W. It has to tilt the vector W to get the correct value. So it will, this algorithm will tilt your hyperplane like this. So if your data has a misclassification, then it changes according to a error. Each update your vector. So my aim is to find out this vector. So first I initialize one vector. If your data gives a misclassification, you are going to update the vector. So first I have to work with all the data. That is the first iteration. Once first iteration completed, so if this is your original, this is your first initialized vector, you are going to get some error. So according to the error, your vector will be updated. After the first completion, some updates has happened. So next iteration, you have to process again all the vector. You have to take the dot product with the new weight. Here this is a vector called the weight vector. So you have to take the dot product with the weight vector. So now if there is a misclassification, again you have to change, you have to tilt your vector according to that. So when we can stop the iteration process, when there is no misclassification in the iteration. When there is no misclassification, you can stop your iteration. You will end up with the hyperplane which classify your data with there is no misclassification. Okay, so now here we have two problems. One is this cannot be applied for the non-linearly separable data. Another one is here there is plane, you are ending with this hyperplane, so that is not optimal. Another one is lacking robustness. To solve these two problems, we have another kind of algorithm, so that is called a support vector machines. So if you learned, if you did any course on machine learning or deep learning, you came across this word SVM, support vector machines. So this will solve two problems. One is robustness, another one is optimization, optimized hyperplane. So next one is the problem is non-linearly separable data. For that, so we have to develop another algorithm that is called the artificial neural network. See that here, this Perceptron algorithm only useful for the linearly separable data. When your data is non-linearly separable, then you have to go for another algorithm. That algorithm is called the artificial neural network. First, we have to introduce from this algorithm. Okay. So now, this is linearly separable data. Another one is non-linearly separable data. So this is the artificial neuron. So here we are getting two input. This is a dimension of the input. Here we are applying the linear transformation. Here this is W. Here, what is summation means? Here, the summation is W1 P1 plus W2 P2. So we are trying to find out the hyperplane here also, but in using the different algorithm, not perceptron algorithm. Here we have to use some optimization algorithm like gradient descent with back propagation. So here, see that this is a hyperplane. Here, this is a step function. For positive value, this will give +1. For negative value, -1. This is the same perceptron algorithm, but in terms of artificial neuron. So if actually here we are going to deal with nonlinearly separable data. So we have to introduce some nonlinearity for that. So we have to apply some nonlinear function of the first can be sigmoid function or rectified linear unit, that is ReLU. So two mostly the important integration functions, one is sigmoid and the one is a rectified linear unit. So first, why we are using these functions? Actually, this sigmoid is a smoother version of your step function. Okay. Certain algorithm is we have step function that is not differentiable. So we cannot use any optimization algorithm because if to apply the optimization algorithm, function should be continuous and differentiable. So we are introducing smoother version of the step function, that is sigmoid function, that is f. Here this is a single neuron. Here this is the dimension of the input. We are inputting the r dimensional input. Here we are applying W1, W2. This is a vector. This is a linear hyperplane, and then applying the nonlinear activation function. This is the output. Okay, here the W is vector with r dimension. Now that is a single neuron. Now we stacked many neurons in a layer. This is called the one layer of S neurons. Here you will get, instead of single vector, here the weight vector is a matrix. And this is the layers of neuron. So we are getting input from here, process through the first hyperplane. We are going to apply many hyperplanes to divide your region, and then nonlinearity. From this input, again we are applying again some hyperplane division, and then again nonlinearity, so on. So here we have 3 layers. So this is a typical one artificial neural network. So next, so why we are calling this is a artificial neuron? So this is a biological neuron. See that here we have a tentacles. So this is called a dendrite. So this is received using this, the neurons will receive the signal from the other neurons. Here this is a cell body. Here it will process all the received signals here, and then these accumulated signal transmitted through axon, and then this is the output. Here from these output, other neuron get the signal. Okay, so actually this is the artificial neuron. See that this is a cell body. Here this is the input, many dimension. It is received from all the dimension. The accumulation happen here, and then applying some nonlinearity. This is a transmission. This is the output. So the structure of this structure resembles the biological neuron. So we are calling this as an artificial neuron. So artificial neuron is nothing but the mathematical computations. So this is a deep neural network architecture. This is the input layer. This is the output layer. So these are called the hidden layer. So we are going to give input here. This is output. This is supervised learning. How you are going to train your model? In the perceptron algorithm, we have some algorithm to update the weights. Here we have to update the weights. Here what is our weights? For the first layer, you will get some matrix. Here for second layer, you will get another matrix. We have to update the weights. First, you have to initialize the weights. This is the input. Process through that, you will get output. But already we know the output, so we have some error. So we have to modify, we have to adjust these weights according to the error. So we have to modify these weights according to this error. So how we are going to modify? This is through the optimization algorithm. We have to reduce the error. So this is a optimization problem. So we have to use gradient descent. So many variants are the stochastic gradient descent and deepest gradient descent or simply gradient descent. So, but to apply the gradient descent, we need the gradient. Gradient means derivative. So here, to get the derivative, see here, this is this is the output layer. Here we have a error function. This error function depends on the weights of the first layer and another layer. Directly, the error depends on this previous hidden layer. And this W1, W2 depends on the another previous hidden layer. So to find out the derivative, to find out the gradient, the error sensitivity is flow from the backward from the backside to front side. So we have a sensitivity, the dependency of the error on the weights is propagating from the backwards to frontward, backward from the backwards. So how to find out the gradient? We are going to use the back propagation algorithm. This is nothing but the chain rule. So once you know the gradient, so you can apply the gradient descent algorithm to optimize the weights. First, you are going to initialize, then according to the error, it will optimize the weights. This is the way to train your model. This is how we are optimizing your neural network. So next, so we are going to see the important variant of the neural network. This is a convolutional neural network. This is convolutional neural network only designed to process the images. So in computer, images are stored as a matrix. So here, this is a 8. So the boxes are pixels. So you came across many times the 720 pixels. The image's resolution is 720 pixels. Here, these boxes are pixels. Each boxes has a number. So this number ranges from 0 to 255. 0 is for purely blacks, 255 for white. So this is the data. This is a matrix for this image. So all the images in the system is stored as a matrix. So this is a black and white image. So we have only one matrix. In the case of color images, we have 3 different matrices. So for one data, so one matrix for red, another matrix for green, another matrix for blue. So here also ranges from the 0 to 255. So if you want at a pixel, the pixel color is purple, then you have to give red is 128, blue is 128, green is 0. So moderate blue, moderate red, there is no green. Then you will get the purple color. This is what your images, color images stored in your computer. So to process the images, you have to process the matrix. So to process the matrix, we are going to introduce another operation that is called the convolution. This is a convolution matrix. So this is the original matrix, your image matrix. This is a filter. So if you are a mathematics student, already you have studied your Laplace transform or Fourier transform or Fourier series. In that you may have some convolution operation. So you have a signal, you have a filter. So it will convolute like in the opposite direction. Dot product is taken from the term wise, but the convolution is in the opposite direction. Here we are going to take the convolution between this matrix and this matrix. See how you are going to take the convolution. This is the element wise operation, and then you are going to take the sum of all this value. So first element, this is 0, this is 1. So 1 cross 0 is 0. This is 0, this is 1. So for this one, so totally you are going to get only one non-zero value. So you are going to store this value here. So next you are going to move your filter is for the next 3 by 3 submatrix. So now take the convolution product, the value is 4. So this is a next convolution, this is a next convolution. So actually here we are multiplying one matrix with another matrix. So what is the use of that? So how these filters are powerful? See here, this is the image. We are applying the filter. Filter is called the edge detecting filter. So what it says? So the filter says that if your 3 by 3 matrix is full of the same equal numbers, so you take some matrix, 2 by 2 matrix. You can take some 3 by 3 matrix full of 2. Then this filter, if you apply the filter, you will get the 0. When you apply this filter, you will get the 0. So if some of the elements from that 3 by 3 matrix is different from other values, then only you will get a non-zero value. So here the picture is very difficult to see that. Here, see that this is full of white. If you apply the filter here, the matrix full of the same color. So there is no changes. When you apply the filter, you will get 0. Here at the body of the dark, you apply the filter. Again, this is full of the same color. You will get the same value. So if you apply the filter there, you will get the 0. So if your pixel is interested at the edges where this dark image and the background images meet, here, if your pixel is here, then you will get some different value. For these colors, different value. For these black colors, different value. So you are going to get some non-zero value for that. So when you apply this filter throughout the image, after that you are going to get one matrix. If you render that image into a if you render that matrix into a image, you will end up with this image. This image is only you have some edges. There is no other things. The colors goes on. This white also, there is no white, there is no black, only the edges we have. This is called a edge detecting filter. Similarly, you have many different filters like blurring an image and sharpening the image. Whatever operation you are doing in the Photoshop, everything is a matrix multiplication. Just you are going to multiply with the matrix, and then you are going to give resultant matrix. You are going to enter into the image. You will get that results. See, now this is a handwritten. How your CNL architecture is trying to understand your handwritten digits. See, this is a 2. So this is a convolution operation. This is max pooling operation. Max pooling operation is just a downward sampling. So here, this is the image. This is the input. This is a convolution operation. This is a downsampling. Again, convolution. This is downsampling. After that, for the classification, you have to use the fully connected layer. See, this is a black and white image. So what is this output layer? Output layer consists of 0 to 9. So totally 10 elements. So how you have to train this model? How you are going to train? This is also supervised learning. You are going to give 2 input, but the output should be 0, 0, 1. The remaining are 0. Totally length is 10, remaining 0. Only this place is 1. So what does that mean? So you're inputting 2 to the 2 as an input. If you're inputting 5 to train 5, you have to give the output vector is 0, 0, 0. First 5 is 0, 6 1 is 0, 1, the remaining is 0. This is the fifth place. It starts from 0, the fifth place is the sixth one, 5 is corresponds to 1. So you have to train many handwritten digits to this architecture. Once you trained many images, so once the trained model is ready, if you write something in your board, it will automatically understand what you have written, how it is gives the output. See that this is your matrix, this is your input, some handwritten digits. It will convert as a vector. This is the first layer, input layer. This will process through all these hidden layers. This is the output. See that this is the output. So what is the greatest value written here? That is the output. If it is a 2, this should be largest value. If it is a 5, this should be largest value. This is what your system understand your handwritten digits. So now this is the image classification for the see how your models understand how it is learns. This is your image. You have to convert this into a matrix. You have to feed as a vector. In the first layer, it will learn the lines and curves. See here, this is the first layer, first hidden layer. This is learned some curves and straight lines. And from these curves and lines, in the second layer, the linear combination of that or non-linear combination, it will try to understand the next shapes like nose, eyes, mouth, and everything is learned here. This is what the second layers do. So now these are the some initial shapes. From these initial shape, it will learn the complex structure like face and all these things. So now this is a linear combination or non-linear combination of this land structure like nose, eyes, mouth. So now it is the third layer land somewhat complex structure. So if you add some more hidden layer, it will learn more complex structure from your image. And the last layer is classification layer. This layer says that, so whether the input is so who is the person, Joe or Chris or Lee. So this is what you are seeing in architecture's works. First you are going to input as a matrix. First it is learn some curves and lines, and then the nonlinear combination of the lines and curves. That is some small shapes. From that shapes, it is again learning the complex structure like phases, and then the final layer is the classification layer. So it classifies. So whether if you input some lion, it will classify as a lion. If you input some vehicle, it will classify as a vehicle. Okay, this is what you are seeing in the architecture works. So now you have some idea about the artificial neural network, how it works. So now we are going to enter into the main objective of my topic, that is graph neural networks. So here we have a difficult structure. Here we have some relations. Okay, these are the different data. So there is no fixed sizes and grids, and there is no topological structures for the graphs. So its graphs are arbitrary size and often dynamic. Dynamic means it is always increase. If you are entering into the e-commerce websites like Amazon, Flipkart, you are going to click, you are going to visit many items. Your graph is always going to enlarge. So your structure is not fixed size. Your graph is not fixed size. So another important problem is there is no fixed ordering in the graphs, and there is no distance and all these things. So complex topological structure. to process the graph neural network, graphs through the neural network, here you need some additional characters. So basic requirements functions over graphs. Here the graphs here don't have any fixed ordering. So first criterion, if you apply a functions land over the graphs, if you apply two isomorphic graphs, it should give the same result. Okay, so this is the basic requirement. For that, we are introducing the two basic concepts. One is a permutation invariant, another one is permutation equivariance. Permutation invariant suggests that your graphs over your function over the graph should give the same result for the isomorphic graphs. Second one, permutation equivariance, that gives that you are able to find out which nodes gives the which output. So you are able to track the output of each nodes. These are the two criterions we have to ensure that before learning a function over the graphs through the artificial neural network. Okay. First, we are going to define the concept of permutation invariance on set, and then we are going to extend that to the graphs without edges. Okay. First, XU be the d-dimensional node features vector. For each node, U belongs to U. So actually, first I define the feature vector for the users and items. This is the XU. I'm going to call this as XU. Form a feature matrix by stacking all these feature vectors. Permutation invariance says that if you learn some function on the graphs, it should give the permutation invariant if all the permutation matrices. If you alter the order of the nodes, it should not change the output. This is permutation invariant suggest. The next one is a generic form for the permutation invariant function. This is a generic form of the permutation invariant function. The psi and p both are independently applied to every nodes. These are the learnable functions. Here, this is the sum aggregated after applying sum over the node feature vector. So we know that sum is independent of the order. So this form of function is invariant with respect to the permutation of the node set. This form of function guaranteed to return always the same output. So no matter how the nodes are permuted. So next one, we are going to define the function on the so permutation invariance and equivariance on graphs. So now we are going to define the permutation equivariance. We say that f of x is permutation equivariant for all permutation matrices. So this says that if you permute the nodes, the vertices of the node, it does not matter if you do it before or after the applying the function. This is a generic form for the permutation invariant function. And the next slide. So we are going to extend the both definition permutation invariant and permutation equivariance on the graph. So this is the updated definition for the permutation invariant and equivariance for the graphs. So this is a GNN layer, GNN architecture that are permutation equivariant functions. So f of x comma a, here x is the node vertices set, a is the matrices related with your matrix, with your graphs. So this local function. So actually I skipped some. So wow. Yeah, here. So we can now generalize the notions of the permutation invariance and equivariance from the sets to graphs in the generic setting. So we are going to implement nodes that is not empty. The graph connectivity can be represented by n by n adjacency matrix. So now we are adding with your vertices set, we are adding some additional structure through the adjacency matrix. In graphs, when we apply the node permutation, we need to appropriately permute both rows and columns of the adjacency matrix. If you apply the permutation matrix P on nodes, changes in the edge set amounts to PA, P transpose. This is updated definition for the functions over the graphs. So now X is a vertices set, A is a adjacency matrix. So now this is a permutation invariance functions over graphs. This is a generic form. Here this is a G is a permutation invariant function. Here X1 is a node. Xn1 is the adjacent nodes, the neighborhood nodes. So if you have the function is here, G is applied individually for all the nodes and stacked as a matrix. If your function is in this form, is ensure that your land function is permutation invariance and equivariance. So this is a GNN layer, typical GNN layer. So okay. So we have many kind of graph neural networks, but we are interested only message passing neural network. So I'm going to explain only that variant. One simple such I don't know how it's this is a neural message passing framework. So this is update function. This is aggregate function. It aggregates information from all the neighborhoods for all the nodes. So update and aggregate is a general form. So they are basically arbitrary differential function. They are learnable function after the training. So okay, this is a diagram which is related with how this is aggregate and update your layers information at each iterations. This is a in general. This is a abstract GNN framework defined into something we can implement. We must give. So these update and aggregate functions in terms of weight matrix. This is one weight matrix. This is one another weight matrix. We are going to learn this weight matrix through the optimization algorithm. So main issues is in GNN. So actually, graph neural networks has achieved a lot of success on graph structured data. One key issue with GNNs is their depth limitation. It is observed that the performance of the graph neural network does not improve as the number of layers increases. When you are deeply stacking the layers, gives some significantly worse performance for the GNNs. Actually, in the deep neural network, you are going to add many layers. If you are in the graph neural network, if you add more layer, you are facing some problems. So first, due to the gradients during the back propagation, another one is overfitting problem. The main issue is oversmoothing. So what is oversmoothing? Smoothing, when you apply again and again the aggregation, you will end up with the similar structures. Like after repeatedly applying the aggregation many times, the future vectors has similar value. So there is no, we cannot distinguish between the nodes. All the nodes has the same kind of values. So this effect is known as the oversmoothing. This hurt the classification performance by causing the node representation to be indistinguishable across the different classes and prevents the GNNs to utilize the higher order neighborhood information effectively. So directions of the work. So this is a main drawback in the GNNs. To address this drawback, numerous approaches have been proposed. Most of them concentrate on the aggregation stage of message passing. The key challenge of analyzing the oversmoothing effect lies in the non-linearity. Over smoothing in ReLU has been discussed by many authors. This is a non-linear activation function. But other non-linearities like sigmoid, tangent, not discussed much. So if you are really interested doing the research in graph neural network, you have to concentrate on the smoothing problem, especially in the non-linear activation functions like sigmoid or tangent. But ReLU has been discussed by many authors. So another some related works I will listed some works has been done. So first author name is these two authors studied the article title is Pair Norm Tackling the Over Smoothing in GNNs. In this paper, they applied the normalization layer in between the intermediate layers during the training. By applying the normalization technique, somehow they overcame the over smoothing problem in GNN's training, but then not for all kind of data set, but for some kind of data set, these idea worked for not all. So next article name, the title is preventing over smoothing for hypergraph neural networks. This paper came out 2022. They developed a new hypergraph convolutional neural network which can maintain the heterogeneity of node representation deep layers. These were published in 2022. They overcame the drawback of the over smoothing by introducing the new convolutional, the deep architecture, the graph neural network. They are introduced another architecture. By introducing the new architecture, they overcame somewhat the disease, but not the next recent paper is came in 2022. The title of the paper is addressing oversmoothing in graph neural networks via deep supervision. So the key idea of this paper is node or graph representation from all layers contributing equally to the loss function. This encourages graph neural network to learn discriminative features at all GNN depths. So using this idea, this is also new kind of variant of the graph neural network. By using this idea, somewhat they overcame the problems during the training of graph neural network. So this is another idea. So many authors discussed these problems recently. So if you look at this over smoothing problem, all the papers related with this came for last 3 years only, 2012, 2020, 21, 22. Many paper came related with the over smoothing over the graph neural network. So actually, if you're really interested in doing the research in graph neural network, so you can look at these areas. This will be very helpful to you. So thank you for your attention.
Thank you so much, sir, for your excellent presentation on neural networking and for sharing your knowledge and expertise with us today. Any questions from the participants? Or any clarification?
We are truly grateful for your presentation and present. We are request you to stay on podium as we would like to present the certificate and a gift to you.